SwayamPrabha. Digital India. Educated India.
So, in the last lecture I discussed about the stability of the phases for pure component system. I took examples of ice and water mixture. As you know, ice, water both consisting of H2O molecules. So, therefore, we consider as a pure component. There are many examples such that pure like carbon. Carbon can exist in diamond and graphite and many other things, but we know diamond is not stable, graphite is more stable. That is mainly because of delta G of both diamond and graphite. If you calculate at normal room temperature and pressure, graphite will have lower value of G of ERG than the diamond. So, this formalism has helped to explain different kinds of stability or different stability of different kinds of phases across the different branches of engineering. Okay, even stability of steam as function of water as compared to water can be explained. Now, question is this: metallurgical world is full of alloys. We are dealing with alloys every day, starting with steels to aluminum alloys to copper alloys, ceramics, they are also alloys. So, we must have a good knowledge of how do we modify these stability conditions for alloys. The real question is that, as I told in the last class, we cannot use the same way whatever I presented in the last lecture for the alloys. So, we have to change. So, to give an idea, this condition is going to be remaining same, this condition will remain the same for universally same for all systems, that the direction of the phase transformation depends on the sign of delta G. Delta G is 0 at the transformation temperature, whether it is a melting, solidification or any solid state transformations, but delta G is negative, then transformation will happen in the preferred directions. If delta G is positive, transformation will not happen in the preferred direction. So, sign of delta G dictates the direction of phase transformation, and I have explained you in terms of water ice analogy. So, now let us see what happens for the alloys. Alloy means you have more than one component, and I gave you an example of if I add salt into water. Okay. You know that if I add salt into water, the melting temperature of ice will increase. Okay. We know that. That is why in the cold countries, when the snow actually covered the roads, to melt it down they sprinkle salt, because salt will increase the melting temperature of ice. So, that is some change because of addition of salt, that is why it happens, and in fact that change is basically happening because of free energy change. Free energy is getting altered by addition of the salt. So, free energy of the systems can be altered or changed by addition of the second or third components, whether we add carbon into iron to make steel, or whether we add copper into aluminum make duralumin. We are changing the free energy of the system. How it is done? First thing you have to understand the difference between a mechanical mixture and an alloy, because I find myself while teaching in lectures in IIT that this concept is not clear for many of the students. As you know, mechanical mixture means what? If I take sand and add salt into it, whatever way I grind it, they will not mix together. That is a mechanical mixture. But suppose if I take milk, add coffee into it or sugar into it, they will all completely mix nicely. In fact, the mixing will happen such nicely that you cannot differentiate between between sugar and the coffee with the milk. In fact, because we add coffee, milk and sugar together, we get a test, different test. That also answers my question that they are atomically mixed. So, mechanical mixture means that I add something into something else and they remain separated, but mechanically get mixed. So, suppose if I have A and B together and amount of B in A is given by the ratio of between B and A is given by x. We will come to know what is x very soon. There is a way of representing x, and 1 minus x is obviously equal to x A, because x is a fraction. So, therefore, 1 minus x is equal to A. So, now if I mix A and B and form a mechanical mixture like that, and then what will happen? If I plot the P energy G, again G is what is important. If I plot G as a function of concentration at a particular temperature, the G of the mixture will be given by the straight line. Why? Very simple. G of A multiplied by 1 minus x plus G of B multiplied by 1 minus x, what is the G of the system? So, I can write down like this: G of A multiplied by 1 minus x plus G of B multiplied by x, sorry, okay. So, that is what is actually, this is the equation of straight line. How it is the equation of straight line? Right, let us write down G of A, okay. So, G of B minus G of A into x. So, this is the G mechanical mixture. So, that means this is y equal to mx plus c, that is a straight line equation. So, this straight line has a fixed slope, that is Gb minus Ga, and it is a fixed intercept, okay. And many times for the pure component, we to separate it out of the mixture, we always write a superscript 0, okay. So, that 0 is tells you that it is a pure, it has not been contaminated by something else. So, the G A0 is what is given here, shown as a mu A0. This is just a symbol, we will explain it very soon what is the meaning of this symbol, okay. That is given by this point. Similarly, on the B side, B is a pure 100% B here, A is 100% B here, and we are adding them together. That is given by mu B0, okay. That is again nothing but GB0 I have written here, because pure components, to separate it out we put superscript 0. So, whether we write in terms of mu or in terms of G, that is not going to change. These are only the conventions. Mu was used by some scientists and it has been accepted across the whole world, that is why we use mu nowadays, but you can use Ga0 also, there is nothing wrong about it. And this is the functions, this is the plot of the function which is given here, the straight line you can see here, correct. So, at a particular composition x of A, x of B actually, and 1 minus x of B A is, this equation is followed. So, I can actually calculate G of the mixture simply by following this line. But you know, alloys are not mixture, alloys are all atomically mixed solution. Solution, what is the meaning of solution? Okay, solution is very simple. If I take water, add salt and sugar, stir it nicely for about 2-3 minutes, it will be a solution, right. And if I add more amount of sugar, there is a limit of saturation, beyond that sugar will not be mixed in water. This all we know from school physics, there is no need of explaining it, okay. So, same thing can be translated in solid. In solid, same situation can happen. I can add carbon into Rn, I can add manganese into Rn and make a solution. So, physically speaking, I am making mixture. Now, the difference between mechanical mixture and the alloy is brought about by the entropy function. That is what the changes happens, okay. And to be frankly speaking, I want to show you this picture. This is a tombstone of Boltzmann, Ludwig Boltzmann, okay. He lived 1849 to 18 something 86, very shortly person. He discovered this entropy S equal to K ln W. You can clearly see it is written on his tombstone, it is so famous function, just to give an idea that this is so important. So, for a solution things are completely different. So, for the next 10-15 minutes we are going to spend time how to explain solution and what is the stability condition for that. Solution means like this, suppose you have A and B, like carbon, Rn and carbon in steel, mix them together, they form an atomic solution. It is written atomic, that means they are mixed atomically. They are you cannot separate one atom from the mixture, they are so nicely mixed. So, what actually happens if I do mixing that? If I mix that, the things which is changed in the G function, G is equal to H minus Ts, the important changes happen is the S, entropy gets changed completely. In a mechanical mixture, they are lying separately, there is no mixture between the two components, they are basically sitting side by side like the students in a class. Okay, if they do not like each other, they never mix each other, same thing happens. So, they are not mixed together. So, if they are not mixed together, there is no change of entropy, because you cannot change the configuration of the system. Entropy has two components, one is the configurational entropy, the other is the vibrational entropy. I am talking about configurational entropy, which is the major part of the entropy change whenever you mix two things together. So, that change will not happen if they are mechanical mixture, but that change will be very seriously affecting the phase stability the moment you atomically mix them together. Okay, so now we can actually, we will go into equation part very soon, but before I do that, plots are always helpful to memorize you, to understand you, to keep it in mind. Remember, equations you have to remind, close your eyes and remind, no, forget it and then you can get it back, but plots, it will remain all throughout your life, that is why plots are better. So, here what I have done, I have again the use of the same plot, phi energy versus composition, here A and B, two pure components, and this straight line tells you my mechanical mixture, phi energy, and this curve which you see here is looks like a parabola, is what is for the atomic mixture or the solution. How does it come like this? It will clear to you with soon from the function, but first initially you accept that this function is like this, because many of the teacher will tell you this is like this only, plus you please accept it. Now, as you clearly see, this is like a parabola, inverted parabola. It starts from pure A, ends at pure B. At these 2 points, both the mechanical mixture and the phi energy of this solution are same. At these 2 points they are matching the values actually, but they deviate slowly as you increase the concentrations, reaching a maximum value, or you can say minimum value, depends on what is the sign, okay, and then it again shoots up, but it is basically inverted parabola. Now, question is this, at a particular composition X, the physical mixture has a phi energy equal to G star written here. You see here, I can simply put a dotted line and find it out, but the atomic mixture has a phi energy given by G within curly bracket within X. So, there is a huge change of phi energy. Delta G m, what is written here is the difference of phi energy between a solution here and a mechanical mixture. That is why a solution is more stable than mechanical mixture, always. That is why alloys are more stable than mechanical mixture. That is why it is easy to make alloys, because it is the phi energy which stabilizes them. Thermodynamically something is stabilized means that this is basically a more stable structure, because thermodynamics tells you in terms of energy perspectives. But I have kept both mu A0 and mu V0 on the both sides, I have not changed, because they are the phi energy of the pure components. Pure A here, there is no B into it, pure B here, there is no A into it, correct? And you can actually similarly calculate any value of X, these values. That will also tell you the relative values of the G. But at any compositions other than pure A and pure B, you can clearly see the solution, atomic solution is more stable than the mechanical mixture. Okay. Then you may ask this question, sir, why sand and salt never mix? There is some other reason behind it. Okay. They do not like each other, that is why they do not mix each other. Now, how do I actually get into mathematically? Let us get into the stability in terms of that, and we will explain what is the meaning of this mu here. Again I have plotted phi energy versus compositions, inverted parabola, I did not plot the mechanical mixture phi energy functions. What I do here, this construction we are doing it without doing mathematics. Please remember, this construction has more far reaching consequences than the mathematics in metallurgy, that is why we are poor in mathematics, but anyway it will come clear to you better. We will do mathematics very nicely and show you how these things comes. So, what I have done, at a composition X, I marked a blob, okay, you see here this is a blob, and then I pass a straight line to this point. That means I make a tangent to the curve at this point. Go back to your plus 2 mathematics, I do not know whether you have studied, but I studied myself. That tangent to the curves can be easily obtained at a particular point, just taking the slope, correct. I can, by knowing the slope, and if I know the two end points, I can easily formulate the equation of the tangent. So, now the tangent actually meets both the pure A end and pure B end. That is why it is written mu A within curly bracket 1 minus x, mu B within curly bracket x, because it contains x whatever fraction of B and x 1 minus x fraction of A. That is why these curly brackets are given like this. So, what is the meaning of this? These mu's are actually known in the literature as a chemical potential. Chemical potential is a really very difficult concept for the students to grasp. In fact, it was also very difficult for me before I came to know much more about it. This equation which you see here can be mathematically written by this G. Suppose this is alpha phase, okay, this is alpha, let us suppose alpha is alpha iron or something. So, G of alpha is equal to 1 minus max of mu A plus x mu B. This equation is same as what I have written here, you see here this same. I can easily write mu A 0 plus 1 minus x whatever 1 minus x of mu x, this is 1 minus x, this top one plus mu B 0 x. This is what exactly same, sorry, exactly same. So, this mu A and mu B, they are not, we have not put 0 superscript because they are not pure anymore, because we are talking about a alloy of composition x, of fraction of x B and fraction of 1 minus x of A. So, we cannot put superscript anymore. So, that means the straight line or tangent which I have drawn, they have this, the equation of this is given by this, correct. That is what you should know. The straight line equation which is shown here is given by that. Now, what does it tells you? It does not tell you anything. It tells you that at this composition, chemical potential of A in this alloy is given by mu A, which is determined by this way. Chemical potential of B, which is given by this point at a composition of the alloy X, is marked by this blob. That is how we can measure chemical potential. But before I go into details of that, let me explain what is chemical potential. Chemical potential will be given in large definition, many definitions in thermodynamics books, but try to understand one thing very clearly. What is the meaning of the word potential? Potential means, suppose if I say you have a big great potential become a professor, that means you have all the qualities to become a professor or all the qualities to become, suppose, Prime Minister of this country. That is what the potential means. So, in physical sense, potential in an alloy or potential in a atomically mixed solution means of a particular component means it has the ability to react, in the system. Okay. If I add something else in the system, it will react, that is the meaning of potential. So, this chemical potential tells me the chemical reaction ability of the component in the alloy, that is what it tells you. So, that means it tells you that free energy is available to do work for that particular component in the system. It has the free energy available to do work. That means for changeover, it has change of free energy is negative for this component in the alloy. So, it can react and then make phase transformation possible. That is the way we can define potential. Otherwise, you can mathematically define it is nothing but change of free energy when you have a big solution added small quantity of component B at a constant temperature, pressure and all other conditions, the change of free energy is basically given by chemical potential. But these definitions are always misleading and this gives you only very difficult way of representing things. The easiest way of thinking is that is ability to react in a particular system. Okay, so therefore, stability of the system can be easily obtained when you have multiple phases, then only we can obtain stability of system, which phase is stable, which phase is non-stable. So, next 5-6 minutes let us do that. So, now let us suppose again I have drawn here free energy as a function of compositions for a alloy with A and B you can see x amount x fraction of b and 1 is x fraction of x, and again free energies are shown here. For the pure, these are the pure A and pure B, because there is, you cannot draw, you can draw a tangent even here, but the tangent will again pass through this point only. So mu A 0 and mu B 0 is for the pure, and these are actually for the component A and B in the alloy consisting of x fraction of B and 1 is fraction of B A, and G is again G curly bracket x. So the condition of equilibrium or stability is given by this. This is again comes from Gibbs. It tells you if I have two phases alpha and gamma, again I will show by plots, but just telling you if I have two phases alpha and gamma, the potential, chemical potential of a component A in alpha, that is why A subscript alpha superscript. Remember this, you cannot interchange these things. Alpha will be in superscript, A will be in subscript. So chemical potential of A in alpha must be equal to chemical potential of A in gamma. Similarly, chemical potential of B, because it is an alloy or it is a mixture solution, there will be two components, chemical potential of B in alpha equal to chemical potential of B in gamma. What is say? Chemical potential of any components, all the phases will be equal. That is what it says. So that is basically a stability conditions. This can be proved. I do not have time and classes to prove that, because this is 30 lecture course, lot of things to be taught. It is there in thermodynamics books, but if you want, we can actually help you in getting the answers in your discussion forum. That can be done. So how can I make it a very nicely and elegant in plots? Suppose I have G, the free energy of alpha is given by this G alpha. You can see this is written alpha, black, both are black actually, one is alpha, other one is gamma. So there are two free energy curves which I can easily obtain from Cp values that I have shown you in the last class. Now what I do a common tangent between them at this temperature T1. Very clearly you see this is common tangent will pass through these 2 points. You cannot draw a common tangent other than these 2 points, because it is a common tangent. Common tangent means slopes here equal to slopes there. That is the mathematical condition. So this is a composition given by x alpha gamma, this is a composition given by else gamma alpha. Now what does it tell you? If I extend these 2 lines, okay, you can clearly see these are the mu values, the chemical potential values. So this is A, this is B, right, this is actually steel, so carbon is written, that is why. So therefore it will be A, Rn and carbon, does not matter A and B, let us consider. So this is mu A alpha, correct, this is also mu B alpha, because this is passing through alpha. Similarly it is also passing through gamma, common tangent, so I should write mu A gamma, and they are equal because they are hitting this y axis on the same point. So this is also mu B alpha is equal to mu B gamma. So you can clearly see this condition what I have shown you earlier, this condition is graphically shown. So therefore this is the condition of stability of phases in a multi-component system or in a more than one component system. Now at any composition x bar shown here, the free energy difference between these two is given by this arrow. These two means what? Free energy of the gamma, which is higher value here, you can see here, and free energy of the mixture of alpha and gamma is given by this point, because this is what is the common tangent line. So this is the difference, this is the free driving force available for the transformation from gamma to alpha plus gamma, okay. That is what is the, this will be discussed in details, how to calculate free energy differences. So in a very simple term, you have got a message that for systems having more than one components, we must look for chemical potential equality for the stability. The moment this equality will not be satisfied, there will be phase transformation. That is what happens in the systems. To give you an example, this is what is not satisfied written when A alpha gamma interface, okay, let me explain that also. This alpha gamma means suppose composition, equilibrium compositions of the alpha phase in contact with gamma, equilibrium concentration of the gamma phase in contact with the alpha, correct. they will remain in touch each other, but their compositions will be different. One composition is here, other composition is there. That is why you have to mark alpha gamma here, gamma alpha there, otherwise it will be confusing. If I put both alpha gamma both sides, it will be confusing, gamma alpha confusing. This is composition of alpha phase in contact with gamma, because they are touching each other. They has to be touching each other, there will be no phase transformation. So, between gamma in contact with alpha. So, these are the equilibrium compositions when the system is at temperature T1 atmospheric pressure, temperature T1 sorry. So, now when this conditions is not satisfied, what will happen? Then this equality will not happen. Okay, these are actually equality in composition. So, therefore, you understand this composition equality is not the condition for stability. This is the chemical potential must be equal across the interface. When this condition will not be satisfied, you will have iceberg in sea water. Sea water is a large source of heat, but still icebergs will sail in sea water. Why does it happen? Because chemical potentials are modified by the presence of salt. That is what I told you, answer I gave you. So, because of the chemical potential modification, because of presence of different salts, the chemical potential equality is satisfied across the interface between the iceberg and the water. And this is the reason, although water temperature is higher than 0 degrees Celsius, you will have iceberg present in the water. And iceberg is dangerous because you know the Titanic, right, that is why. So, these icebergs are present in across the northern hemisphere or the southern hemispheres and near the poles also, even with water. So, we can actually explain the stability of these icebergs using chemical potential equality. This is possible and this has been done by the many scientists. So, in a nutshell, in these two lectures I have given you an idea how to obtain the information regarding stability of the phases thermodynamically. This is very important, but this only tells you which way the reaction will happen, transformation will take place. It does not tell you how fast or how slow the reaction or the transformation will happen. This can be obtained only by understanding diffusion or the movement of the atomic pieces across the interfaces. That is basically not done by thermodynamics, that comes from the idea of diffusion. So, slowly after maybe 1 or 2 more lectures we will get into diffusion, and we need to discuss about the interfaces when you talk about diffusions.